More examples. A realistic example, in the University of Pittsburgh Benedum Laboratory building, there is a display by Alcosan where they build aluminum cans. They show you the billet drawing procedure, how you take a flat piece of aluminum metal, draw it into a can shape, and prevent pressure from building up and blowing the can open. Let's make cans. I want a 1 liter can. I want it to be a cylinder. I want it to use as little material as possible. Because if I'm Alcosan, I sure as hell don't want to make, I sure as hell don't want to make, I'm sorry, if I'm Alcoa. Alcosan's the garbage people, sorry. If I'm Alcoa, I don't want to spend a whole lot of money on the aluminum cans. I want to make them as cheaply as possible, sell as many of them as possible, make some money. So, if I want to minimize the cost of the materials, I want to minimize the amount of material used. That's why I'm assuming a constant price for all the different pieces. The top, the bottom, the sides, they'll all be the same cost this time. So, my question to you is, what's the formula for the area of a can? Here's again where I told you I might need outside knowledge. Can's a cylinder. Aha. A cylinder, circle top, circle bottom, and a rectangle for the sides. So, let's picture our cylinder. And I need some dimensions for this cylinder. Let's label things that will help me for the area and the volume of a cylinder. Circle, I'm going to need a radius for a circle. And then the cylinder itself has a height. Great. The top and the bottom are circles, so I'm going to have 2 circles. The formula for the area of a circle is pi r squared. What about the rectangle? Side. I'm just looking at area at the moment, because that's what I want to minimize, right? The area. So how do I figure out the area of this piece? But the width isn't straight in that picture. The width is the circumference of that circle. Because when I take this and I slice down one side and I unroll it, the width of this rectangle is the circumference around the top. Distance around a circle times the height, length times width. Perfect. This is my area. But I do still need the volume, because this expression has two variables in it. If I'm going to do calculus, I'm going to do calculus in one variable. I need to go from 2 down to 1. I need some other way of relating radius and height to each other. Here's where I can use the volume, because they've told me something about the volume of this can. It's a liter. What is the formula for the volume of a cylinder? I take the area of that base and I picture it stacked up over and over and over. I picture that cylinder as if it is a stack of circles. So I take all of the circles going up and I add them up. I'm going to have h of them going up. I multiply by h. Now I come to a problem. The volume of this can is a liter. What units are R and H in? I have the foggiest idea. We haven't decided, have we? Say again? No. But if I'm using liters, I should be using metric units somewhere. I shouldn't do this in feet and inches, because I don't know how to go from liters to feet and inches. Doesn't make any sense at all. Can. If I was going to measure that can in your hand, what units would I use to measure it? Metric units. Right? Most likely. Centimeters. If I do that, centimeters times centimeters times centimeters, oops, centimeters cubed. I shouldn't use 1. I should use cubic centimeters. How many cubic centimeters in a liter? Dr. Zegan's going to beat the snot out of all you people in her lab classes. How many cubic centimeters in a liter? I don't know. You tell me. Say again? 1,000. 1 centimeter cubed is 1 milliliter. So a liter is 1,000 of those. A milliliter is a cubic centimeter. So if I set this up, then I know that R and H are in centimeters. Now look at the formula for area. The formula for area has R squared and RH. That's going to give me square centimeters. Good. That's a measure of area. Do the dimensional analysis first. Make sure you're working in the right set of units. Now then, how can I use this to fix this? I can get H all alone. As soon as I divide by R squared, I am assuming that R is not 0. But I'm pretty sure I didn't want to use R equals 0 anyway. If a can has radius of 0, here it is. Okay. But that means that R is a positive number. I don't know how to make a can with a negative radius. Now I can put that back up in here. And my area expression becomes solely in R. Yes, now we simplify algebraically. Then we can do the calculus we want. I now have a function of R. I want the minimum area. So take a derivative, find me some critical numbers, show me what we have as a minimum.
This is in terms of R.
Say again? I'm up here, you're over there, you're talking quietly, I'm partially deaf, you got to speak up a little bit. Good. This happens often, by the way. By formulating the question and starting to ask it, you start to think about it and you answer it. That's a good thing. Ask the questions. I take my derivative. I think it will be easier to do the algebra up front. That's my opinion, but you don't have to. I'm going to find a common denominator here. This is going to go over R squared. If I want that to be over R squared, the top is going to become perfect. Again, I need critical numbers. I need to know where either this does not exist or where this is equal to 0. There is clearly a place where this doesn't exist. But we already ruled that number out, right? Up here. So I really don't have to worry about that one. While it is a place where my derivative does not exist, it is not a critical number because it is not in the interval we are going to look at. On the other hand, it's equal to 0 there. (2,000 divided by 4 is 500. So I'm going to take the square root of that to get R. The cube root of that. Again, I don't know what this number is, but I can ballpark it. 500, pi is about 3, 500 or 3 is 160 something. The cube root of 125 is 5, so this should be a little bit bigger than 5. Angela, you're now nodding at me. You have a decimal? Good enough. How do I know that this is a minimum? But that equation here, that's the original equation, right? Part of it's a parabola, but part of it isn't. So I can't quite use that argument. But I could use something similar. There are two different ways for me to tell if this is a parabola. Sorry, if this is a minimum. Second derivative or with the first derivative. You can either make a sign chart, show it's going down and then going up. We'd have a minimum. You can do a second derivative. Tell me it's concave up. We'll have a minimum. Whichever one you want to do. I haven't done the second derivative yet. Let's do the first derivative test. So I pick a number smaller and I pick a number bigger and I go to 10. I'm not worried about anything over here on the other side of 0 because we said R had to be bigger than 0. I don't know how to make a can with a negative radius. If I put 4 in here, or I can put it in here, either way, 16 times pi minus 2,000 over 16. Positive or negative? I need to check. 4 times pi times 4. Is this part, and then 2,000 divided by 16. $200 divided by 16 is 2,000 divided by 16, 125. 4 times pi times about 50-ish, 50. This is a negative number, right? If it's negative, we're going down. That's a good thing. Put in 7. That one's positive. We're going up. We must have a minimum here. Which is what I wanted, right? I wanted the minimum area for this can. Have I answered the question? Why not, Nicolina? I only have the radius. I want both dimensions. Find the dimensions that minimize the cost of... I need the radius and the height. What's my height? I have that number, don't I? I have a formula for that number right here. It's almost exactly twice the radius, isn't it? Twice the radius is the diameter of the can. The can should be as wide as it is tall. It should look like a square. Now you'll notice this assumes that I'm not worried about any materials strength or anything like that. Soda cans, energy drink cans, they're not round like this with flat tops and flat bottoms. What do you see as you get closer to the top or closer to the bottom of the can? Bunch of curves, right? Those curves and the curve on the inside of the bottom, those are designed for the pressure because the contents of that can are pressurized, right? I need to take that into account. Coca-Cola redesigned their soda cans about 10 years ago. They increased the radius of the curvature on the bottom. The bulge that goes in and the bend around the bottom of the can were both made more concave. You know why? They could then put 5 milliliters less of soda per can at the same materials cost. Surprise! Now, depending on the problem, these may or may not have real physical relevance. This problem sounds absolutely stupid. Here's a line. Find the point on the line closest to the point -3, 1. Solving this problem is the beginning foundation of data analysis. I'm only allowed to use points on the line. I want to get as close as I can to that answer. I'm only allowed to use points from my building blocks. 6x plus y equals 9 to get to this one point, which is not on that line. Finding the point of closest approach sounds like a strictly geometric idea. Every single data analytics question you're ever going to answer in statistical analysis, in linear algebra, in all sorts of places where you're doing the statistics for that, you can use this idea. Draw me a picture. I drew a picture for the can. I drew a picture for all of the stuff I did last week. Let's draw a picture here. Imagine you are standing at the point -3, 1, pointing at the line, right? Trace your finger across that line. At some point, you're as close to the line as you can be, right? I don't know where that is. Somewhere there's a point where I'm as close as I can get. How do I measure distance? That's slope, unfortunately, rise over run. And I'm not sure that's going to help me here, but it's not a bad idea. There are ways to solve this problem using the slope, but I'm looking at distances. I have 0.09, but I don't know that that's the closest point to negative 3, 1, do I? So I could use the slope and the point, but I don't know what the slope is to go to get to the closest point. Well, distances in x is only the horizontal distance. I want the distance to the line. That might not be horizontal. Well, if I plug in negative 3, 1, I'm not going to get 9. Derivative helps me maximize or minimize. I need to know what the derivative of what. Okay, that's the distance between 2 points. I hate working with this square root. It turns out, because I think of distance as always being positive, that if I want to minimize this expression, I can minimize its square. The reason I knew that is because for positive things, the square root function is always increasing. And when you have a monotone function, it's always going up, you can use that as a transformation. So instead of just looking at this d, I'm going to look at its square. And if I can minimize that, that's good enough. The reason for that is a theorem from a guy by the name of Lipschitz, and we're going to worry about that in our functional analysis class much, much later. So I promise this works, trust me, for the moment. I now need to somehow involve my point and my line. I agree with you. We should be screaming about this. How do I change this equation to involve my point and my line? If I plug in the point, I get this. But that's still a function of 2 variables. And that makes me unhappy. How do I fix that? Remember, we have the equation 6x plus y equals 9. So I write y equals 9 minus 6x. And then I can turn this into something that's just an x. Our function of x looks like that. That's my distance function. Well, squared. Minimize that. Again, you have your choice. You can do algebra up front, multiply that whole thing out. You can use the derivative by using the chain rule. That's fine. You can do it either way. It's up to you. Regardless, you're going to take the derivative. You're going to figure out where it doesn't exist and where it's equal to zero. Give me critical numbers. I decided to do the algebra in advance, multiply this out at the beginning, take my derivative, and that's polynomial. It's never undefined, but it's equal to zero exactly once. How do I know this is a minimum? This one's type. AJ, now f of x is a parabola.
So it's
And that's opening up. So this critical point must be at the bottom. My second derivative is 74. 74 is positive on concave up. This is a minimum. Have I answered the question? Why not? And a point needs both an x and a y. But we have the expression y equals 9 minus 6x. So y equals 9 minus 6 times 1.22, which is roughly 1.7. And so my point is 1.22, 1.7. Ta-da! Again, a problem that sounds stupid. Example 4, page 340. A woman launches her boat from point A straight across a river 3 kilometers wide, wants to reach point B, 8 kilometers downstream across the bank, as quickly as possible. She could row across the river and then run. She could row to some point between and then run. The rates are different. She can row at 6 kilometers an hour and run at 8 kilometers an hour. Where do you go? I don't give a flying at a rolling donut about running down a riverbank. Let's take this same problem and turn it into a cost problem. I need to run internet cables, data cables across the river. Going across the river is expensive. It costs me $1,000 a kilometer to go across the river. Running them along the riverbank is a little cheaper. It's only $800 a kilometer. Where should I go across the river to minimize my cost? She's going to try and minimize her time. I'm going to minimize my cost, but it's the same idea. Where do I aim so that the net result is as cheap as possible? If I spend a little more going across the water, because instead of going 3 kilometers, I go a little further, then I'll spend less on the riverbank. Maybe if I go straight across, I'll have to spend more. That'll be 3 kilometers this way. That's 3,000 and 6,400 because it was 800 a kilometer this way. That's $9,400. Maybe if I go down a kilometer diagonally, like at point D there, maybe I can figure out how to make this cheaper. Turn this into city blocks. I need to run water pipes. Where do I run them? I've got the lovely A-lot. And I have to run electrical wiring from this side, where admin is, to Lynch and Boyle. Where do I rip up the street? Because it's going to piss everybody off with A-lot torn up. Where do I rip up the street? Same question. This should be a familiar picture to anybody who's taken a physics class. I have a beam of light for going from the air to the water. What happens? It's refracted. And Snell's law tells me that the sine of the angle we make with the vertical is proportional to the speed of light in the air versus the speed of light in the water. If you take the speed in the air, divide by the speed of light in a vacuum, you get some number, usually called the refraction constant, coefficient of refraction, or the refraction index. Air versus water. So you won't always see this with V1 and V2. Sometimes you'll see it with N1 and N2. Guess what? It's the same bloody problem. as the woman in the boat, as me running cable, as me figuring out where to rip up a lot. They're minimizing the time spent. The goal is for light to move as fast as possible. But when you hit water, you hit more atoms. What happens when light hits something? No, at the molecular level, when a photon hits an atom, not necessarily, it's absorbed and then re-emitted, right? You absorb the energy and then you spit it back out. Do you know what that does to the atom? That's energy to the atom. So it wiggles a bit. If you think of water as a bunch of polar molecules all linked together, all you chemistry people, here's a solution. The polar behavior creates little springs between the molecules of water. And they vibrate. And things bouncing on springs use energy and give you trig functions and sine waves. And thus the light bends because it's being absorbed and re-emitted and absorbed and re-emitted. And it turns the light. And based on the frequency of that light, the energy it brings, they create different wiggles. And that's why you get rainbows. Because the different frequencies of light bend differently. Ladies and gentlemen, calculus gave us the rainbow. Newton's first book that used calculus wasn't his calculus book, the Principia Mathematica. It was his book on optics. Calculus was an appendix to that book. Useless. I'm never going to use it anywhere. Optical polarimetry, chromatography, they're all based off this idea. I'm alive because we can do these analyses. Medicines work because we can do these analyses. Useless. All I want you to be able to do is figure out what we're taking the derivative of. And even if the problem sounds rigged and sounds dumb, there's an application to it that's really weird. And depending on the way we do the problem, we can learn different things. Example 5 asks me to inscribe a rectangle inside a semicircle. That seems really weird. I've got a half a circle, and I want you to put the biggest possible rectangle in it you can. Huh? Well, there are two different ways to do this problem. And the first way needs the equation of the semicircle. What's the equation for a circle? Nope. The actual geometric equation for that circle, the graph of that circle. X squared plus y squared equals the radius squared. I only want the top half, so I can rewrite that as y equals, right? Well, then I have a relationship between x and y. And I can make a point. And then I can figure out the area of that rectangle is 2 times x times the y value. That's a function I can write all in x, and I can minimize it. I can also do this with some trig by looking at the angle that I go at. There's another solution, which, by the way, is easier. Why is it easier? Because there's my area equation. And taking the derivative of that's going to suck. But this equation is just trig functions. And I know how to do the product rule of trig functions. It's easier. So depending on the way we think of the problem, the approach we take, there are different ways to do the same problem. Each of them teaches us something different about how to approach the next problem. You should take a look at all of the examples in this section carefully. I know there are only a few homework problems, but they'll all be worthwhile examinations for you. Monday. Monday's the end of chapter 4. That makes Wednesday the review day, Thursday the day the homework is due, and Friday the exam day. Because trust me, you don't want more stuff on this next exam. So, on Monday, we're going to do it backwards. I'll see you then. Enjoy your weekend. Happy Halloween. And I'm terribly sorry you weren't there for dinner last night. Happy Halloween from the math department.
So,